Okay. Okay, hello everyone. I think I should start now. So welcome to the 33rd RQC Colloquium. So it's my pleasure to introduce Professor Don from UTS, University of Technology, Sydney, and also Australian National University. So he is an expert in theory of quantum control optimization and also machine learning. And also he is my long-term collaborator. So he received his PhD in engineering from University of Science and Technology of China in 2006. Then I think he was, he had a lot of affiliations, but he was mainly at the University of New South Wales for more than 10 years. And then he moved to the Australian National University and very recently moved to the UTS. So he also has a visiting position at RIKEN more than 10 years ago. So he knows RIKEN well. So, and also he has a lot of awards and also fellowship, such as a feature fellowship in Australia or Humboldt Research Fellowship in Germany. And also he has been actively involved in IEEE as an editor. Okay, so the title of his talk today is Optimization and Analysis in Quantum Tomography and Quantum Encoders. Okay, please join me in welcoming Professor Darwin Don.
Okay, thank you. Okay, thank you. Yeah, here there's nice introduction. So it's very glad to come back to visit RIKEN. I think this is my sixth time to visit RIKEN. And today I will introduce some work on quantum tomography and quantum autoencoder. Work. Okay, so this is the outline of my talk. And first I will introduce a little bit background, and then I will introduce quantum state tomography, detect tomography, and Hamiltonian identification and process tomography. So after that, I will introduce quantum autoencoders. So, the quantum technology, they have lots of potential for future applications. So, of course, here, RIKEN have a very good development and make a lot of pioneering contributions. And they have so they in the last 10 years, especially for quantum computing, they have very good progress. And another application is quantum sensing. So this is I think in Japan, in RIKEN, they have a lot of very great progress. And what we consider is first problem is the quantum tomography. They related to the first three postulates of quantum mechanics. So for example, the first one is how to describe the state of a quantum system. And this is related to quantum state tomography. And the second one is how to describe the evolution of a quantum system. And this is related to, like, for example, identify Hamiltonian process. And the third one is how to describe measurement. Basically, this is related to quantum detect tomography. So we will introduce today. So mathematically, you can see here, for example, for state estimation. So sometimes I use estimation and sometimes tomography, sometimes identification, because my background is control theory, and they often use estimation identifications. So for the quantum state, so mathematically they should satisfy these three conditions. So first, the rho should be Hermitian, and they should be trace should be 1, and this is the so it's yeah, positive semi-definite. And for the detector, normally we can use like operator POVM to describe the detector. And here also they should satisfy the, these conditions, constraints. So they have, of course, if we know, for example, the measurement, the P operator, the detector, and if we know the state, and we can calculate the probability, PI. And similar for if we state, and we try to estimate state tomography, we try to estimate rho, but for the detector tomography, we try to estimate this the operator. So another is the process tomography. And this we have, for example, we have a process and we have input state and output state. And we use this input state and the output state to estimate the process. Of course, they should satisfy some constraints. So yeah, now we will introduce first consider the state tomography and then detect tomography and then process tomography. So here is two examples to like make measurement to get the data. So for the state tomography, so we, of course, the aim is try to reconstruct an unknown quantum state. So the typical method is we have a lot of copies and make measurement, and then we can estimate, reconstruct the state. So for different from the classical system, when you make measurement on quantum systems, and they will change their state, and so we need a lot of copy. And for good algorithms, so we hope this method they can achieve high level of accuracy, and they have low computational complexity, and also we hope we can guide how to choose the measurement, because for different measurement also in the experiment, some measurement is easy to realize, but some is difficult. So because this is you can see this is a very fundamental task. So of course they have some existing method. So two widely used method is one is the maximum likelihood method. So this is still the most popular method. And another is the base mean estimation method. So both of them have very high computational complexity. So for example, for 9 qubits and use a like normal laptop, maybe take years. And we propose a linear regression estimation method. And for example, if we mention for a density operator, so they should satisfy these three conditions. And the method we use, first we can choose a Hermitian basis, omega I. If the dimension of the quantum state is d, so we choose this kind of Hermitian basis, omega I. So they have a d square basis. And after that, after we choose this basis, we can expand any quantum state with dimension d is like this. Use this Hermitian basis omega I. So here d is the dimension, I is the identity matrix, and the theta I is a coefficient. So if you know this state and you know the Hermitian basis, you can calculate the coefficient. But here, of course, our aim is to try to estimate rho, so we don't know rho. But if we can estimate the theta I, and then we can reconstruct the rho. So this is the basic idea. So now we need to estimate the coefficient theta I, theta 1 to theta d squared minus 1. After that, we can estimate the state. So what the advantage use this Hermitian basis, you can see here, after we choose the Hermitian basis, they automatically satisfy the first two conditions. So the automatically get trace equal 1, and it's a Hermitian. So after we get estimation, we just need to ensure this is a positive semi-definite. Of course, here we try to get the estimation. We need to make a measurement, and we, for example, we can choose a measurement basis, and the measurement basis up to this one. So this is correspond like a measurement operator. So because this is a measurement operator, also can be expanded use this Hermitian basis or omega I. So after we choose this Hermitian basis and the measurement operator, we can know this is the coefficient because we can calculate to use this similar as the Bourne's rule, right? And if we choose this Hermitian, the measurement, and we choose this the Hermitian basis, so basically we know everything for this relationship. So now use the Bourne's rule, so we can calculate the probability to get some result when we make measurement. So this is the state, this is the measurement operator, and we can calculate the Pn, so the probability to get this result. So use the above the representation, so we can get this relationship. This is the Pn, the probability, the equals this one. So here D is dimension. So the theta I is the coefficient we try to estimate, and the percent I is the coefficient in the measurement operator. Okay, so the now we need to get the probability, right? So for the experiment, normally we can, for example, we can do many times the measurement, and we can calculate we can get the frequency to get that result. For example, here we consider the total measurement is a capital N, and we have like M operators, measurement operator, so we can equally divide by, for example, the total number by this number of measurement operator. So then we can make the measurement, and we can count, for example, the frequency to get some result. For example, this is the like P Polaris result, or S Polaris result. And then we can use this frequency to estimate the probability. So according to the central limit theory, we know the error between the frequency and the probability of this is a normal distribution. So the mean is 0, and we know the variance can describe you this one. So now we can describe this as Pn hat. Basically, is from the experiment data to estimate the probability, and equals this one. So the D is dimension, the theta is the parameter we try to estimate, and the percent is percent N basically is the coefficient in this measurement operator expansion. So the theta, the En, the error, we can think about this as a noise, and then we can, after we get this equation, we can easy to solve this equation using, like, for example, a different way, like least square method. So we can characterize the computational complexity for each step. So the total computational complexity is OD to the power 4. So our original motivation is try to develop a more efficient algorithm to do the quantum state tomography. But for the most popular method, the maximum likelihood method, we don't know what's the computation complexity. So we can compare use the like numerical method. So for example, here, the x-axis is the number of qubits, and y-axis is the time to reconstruct the state. So this is the blue triangle is maximum likelihood method, and a blue circle is our least regression estimation method. So roughly speaking, our method is like 10,000 times faster than maximum likelihood method. So of course, for estimation method, the efficiency is important. Another is the accuracy also important, right? So we compare these two methods, and our method is the estimation error is larger than the maximum likelihood method. So here is the mean square error, but still this is our method. This is the maximum likelihood method. So, but this is still quite good for the accuracy is quite okay. So you can see here we just simulated to 6 qubits for the maximum likelihood method, because at that moment they use the laptop, they will already take more than 1 day. And if you increase 1 qubit, they maybe take more than 10 times time. So the question is when I think this is a basically is a homework when I introduced the method when we visit Riken, and yeah, Frank Laurie gave me this homework. So that's the how many qubit we can reconstruct use our method. So we, if we, that moment, the maximum, I think the world record for entanglement in experiment is 14 qubit. But now, of course, it's the much higher. So the if we directly use our method without optimization, so the computational complexity and the storage requirement is order of the 10 to the power 19. So it's still impossible. But we find we can do some optimization, and we can reduce the complexity for order and storage requirement for line order. And after that, we can use the GPU parallel programming, and we can complete the full reconstruction of 14 qubit within 4 hours. So that's the one. So how, for example, that moment, yeah, how, for example, how many qubit we can reconstruct. And another is of course, because our method, the accuracy is worse than maximum likelihood method. So what we try to improve the accuracy. So we develop an adaptive method to increase the accuracy. So for example, the idea is like this. So if we have like 10,000 copies, and we get the data, and we can do the estimation and get the estimated state. So another way we can, okay, so first we use the 10,000 copies, but first we just use like 5,000 copy and get a rough estimation, and then we can optimize the measurement, and we try to find the best measurement to attract the information as much as possible. So in that way, we still use the same amount of measurement copies, but we can get a better estimation accuracy. So of course, we need to find a way to optimize the measurement, and yeah, so I skipped the details, but roughly speaking, it's okay. So the idea, we have new measurement come, and the new data try to reduce the estimation error as much as possible. So in that way, we can find the best measurement. So we numerically compare the different methods. Here we consider two kind of adaptive measurement method. So the red one, the blue one is our method. So the x-axis is a log of number of resource copies. For example, 4, this corresponds to the 10,000 copies, and the 6 correspond to 1 million measurement, 1 million copies. So the y-axis is log of infidelity, and basically the kind of measurement accuracy. So here we compare several different methods and for 2-qubit system. And this is a non-adaptive method. And roughly speaking, so our adaptive method is can achieve a much higher estimation accuracy. So what's the difference between the red one and blue one? So the red one is they just can use the local measurement, but this is the blue one. They can use it, for example, joint global measurement. But of course, in the experiment, the global measurement is much harder to realize than local measurement.
What is GM bound?
Okay, a good question. So this is the So this is it's like a bond for you. Similar is a chromosomal bond that's used in like quantum information theory. So this bond is it's a bond if we use like a unbiased measurement, but here is because the adaptive method, we use the adaptive method. This is it's a kind of biased measurement, so they can break that bond. Yeah.
And with adaptive measurement and without adaptive measurement, the power looks different, right?
Yeah.
So what's the power and why it's different?
So this is you can see this is a scaling is achieved like a little bit like the I think the Heisenberg limit, and because this is 1 over n, and this is the like 1 over n square. So our collaborator at the USTC, so they implement experiment and to verify this scheme, and they roughly speaking, this is the 2 parts. One part is to prepare the state, and another is adaptive measurement. So this is a 2-photon quantum state. And here is the experiment result and the numerical result. So this red one is our adaptive measurement, but just use the adaptive method. And this one is the non-adaptive method. Yeah. And the orange one, we just do the simulation because this is the map measurement, and this is the involve like entanglement measurement. So it's sometimes it's hard to realize. So roughly speaking, our experiment result, the data is a match with our theoretical results is quite well. So another is
but the data with adaptive measurement, why do you have those different slopes?
Okay, that's a good question. So this is because you know, this very depends on how many copies, and for example here, so the first part is for different copies, like they have sometimes they you know, so when you like estimate the state, so sometimes they for very small eigenvalue, it's very hard to like estimate. But after you have like some, for example, copies here, so let's maybe compare the estimate error is not significant. So it is a, for example, this part may be the very small eigenvalues dominate the error, but after you have a sufficient number of copies, that may be the other, for example, error dominates the this is the accuracy.
But at the small n limit, why the slope is different?
You mean this part?
Yeah.
So I think it's they have like a different. So here I think the reason is because the copy number is quite small. So you know I think this is three different kind of dominant error. So this part, you have not sufficient number of copy when you use the probability, the frequency to estimate the probability that dominate the error. So this they have this kind of slope. But this part, because the small eigenvalues dominate the error, and this part is you know because the error for example the measurement they dominate the error. Yeah. Okay, so now I'm introduce some result on quantum detector tomography, and yeah, maybe I should update the experiment system with recons. This is basically I get from Hero. So this is the quantum optical lab at the USW. So they, for example, they try to calibrate the quantum detector. And this problem, we can formulate into a mathematical problem, optimization problem. So basically, we give probe state, and so, yeah, for example, this is a known. And the experimental data, because we get the, after get the measurement, we get the probability. And then we try to solve this optimization problem. So this is the measurement data, Pij. So this is the height is estimation from the from the frequency, and this is true. This is the like P hat is the PVM to characterize the detector. We try to estimate. So rho J is input state. What we call probe state. So of course, this is the PVM should be satisfied this condition. So we can convert this problem into a linear regression problem and solve it using a two-stage approach. So the first stage, we ignore the requirement, the positive semi-definite requirement. And then the second stage, we consider this is a requirement. So they can. So the advantage is that we use this two-stage method is we can characterize the estimation error of our algorithm, and also we can calculate the computation complexity of this kind of computation complexity. So use this method, we find this is the final estimation error basically between the true value Pi, so this is POM to characterize the quantum detector, and the estimate E hat, they get us this one. This is the error bounded by this one. So here the D is the dimension of the system, N is the number of the detector POM element. So N is the total number of resources. So this is a we collaborate with Hero and Shota. So the we can see the left side is a simulation result. We try to show the advantage of efficiency. So the x-axis is the number of qubits and the correspond to the dimension. Of course, the y-axis is the log of the time. So the red one is basically the estimation error. So when we compare with the most popular maximum likelihood method, MLEs, we suppose the two methods have very similar estimation error. So then we compare the efficiency. So this one is our method. This one is the blue circle is the maximum likelihood method. So you can see, so our method is much more efficient than the maximum likelihood method. So the right figure is the result compare experiment and simulation. So we use the experiment data from Shota and Hero, and we find this the experimental result is matched with the numerical result very well.
Why this curve has such a
Oh, you mean this one?
Yeah.
Yeah, a good question. For this one, I mean, not very sure. Maybe it's a similar situation or yeah. So I'm not sure this is a because this have similar skin, but not sure that's the.
But at least simulation reproduced it, right?
Yeah, so the simulation and the experiment data was matched.
But you don't have say qualitative explanation.
Yeah, because this one I'm not very sure. But for that one because we do lots of simulation and we check and we find because the error is dominant error is different from different resource. Okay, so another way is we can design optimal input states, and we can develop adaptive method to enhance the estimation accuracy of a detector. So the idea is similar. So for example, we design some like a proper state and make measurement, and we estimate the PUVM of a quantum detector. And then we can use the rough estimation, we can find the best proper state. And then we can use this, we can use the same amount of measurement to get the better estimation of the detector. And also we can use other method, for example, other technique to enhance the estimation accuracy. So for example, we can use a regularization at this 10 to enhance the estimation accuracy. So this is a regularization, is a very popular method in machine learning to improve the accuracy. So of course, they can, for example, this D matrix, you can use a different kind of D matrix. They have a different performance. And we can characterize the scanning of the mean square and find the best regularization.
Question. So here you characterize a detector by tomography.
Yeah.
And with this adaptive method, are you changing the detector adaptively? Or?
Yeah, that's a good question. So here we didn't do that. So that's recently we consider that problem. So here we just change the proper state, input state adaptively.
Input state. Yeah. Okay. Yeah.
So that's a good question. So that if we can adaptively change the detector and the proper state, maybe we can get a better performance.
Right, but my question was that, when you characterize a detector, and if you change the detector, I don't know what. But
here we didn't do that.
Okay.
But for theoretical, in principle, we can find whether that way they can get the better performance.
Okay. So usually for the Q quantum detector tomography, the probe states are some particularly chosen states, or you are sending just random states, or
That's the, so for this theoretically, like for example, if we want to check the best performance, we suppose any like random input state we can choose. But if we give like a specific input proper state, and maybe we can get the limited performance. Yeah, but for practical situation, maybe that's more practical. Yeah.
I see. And then in the adaptive case, you can choose the probe state, change the probe states.
Yeah.
I see.
So like when consider adaptive state tomography seminar, so when we try to find the limit, so we normally suppose any measurement we can generate, but of course for the experiment we just constrain to some specific measurement. Okay, so next part I will introduce some results about the Hamiltonian identification or process tomography. So the first is try to estimate the Hamiltonian, so because that can be a special case of the process tomography. So the idea basically is that we have a known Hamiltonian, we give some known input state, we can do quantum state tomography on the output state, and we can reconstruct the output state, and then we can estimate the Hamiltonian. So here, of course, this also is a fundamental problem, and they have some existing result, and we try to develop some new algorithm, and we hope our algorithm can be more efficient, and also we interested to do some error analysis. So we propose a two-stage stage optimization algorithm. So we have, for example, input state to the Hamiltonian, we get the output state, we make a measurement, and we can convert this, get the estimated output state, and then we use a several step transformation, and we try to establish a relationship between the true Hamiltonian and the estimation Hamiltonian. So I skip this detail, but here I give a little bit more introduction for the each steps. So the step one, basically do the quantum state tomography, and 2 and 3 basically do some linear transform. And we try to establish a relationship between the true value and the Hamiltonian edge. So they have established some relationship. And then we do some like a two-step optimization. And then we try to construct the Hamiltonian here. And why we like decoupling this into multi steps. So the reason is that we want to characterize the computation complexity. We want to bound the error. So if directly one step, okay, so you can't get the analysis result. And we get this error bound if we have, for example, this is the edge is Hamiltonian, and the edge hat is the estimation. So they can bound to use this relationship. So the D is the dimension, and the capital N is the number of resources, the state tomography for each output state. So we do some simulation for example, for this is the 2-qubit Hamiltonian, and we compare the numerical result with the theory, and basically the numerical result is matched with our theoretical result very well. And also because our original motivation is try to develop more efficient algorithm. So we compare with other method in this PIL paper. So this is use a transformation, I think a transfer function method So this is the red one is their method. The blue one is our method. So this x-axis is number of spin. We consider spin system this kind of Hamiltonian, and the y-axis is the log of the t. So you can see, roughly speaking, for 3 qubit system, our method is 10 times faster than their method. For like 5 qubit, our method is 1,000 times faster than their method. So that means for our method, if they have like a good advantages for high dimension systems. Okay, so another one is for quantum process tomography. So we propose 2-stage solutions. So here, for example, we have a quantum process, and we try to estimate the process, and we give this input state, we get output state, we can make a measurement, and then we can reconstruct the output state. But here we find we don't need to really do the full reconstruction for the output state, and we don't need to ensure that they are like a positive semi-definitely. So then we use this data, and we can reconstruct the process. And here, so we can get a closed form solution. And also this could be used to trace position and non-trace position. So also we can characterize the computation complexity and error upper bound. Of course, for this tomography, process tomography, also we can do optimize design, find the best input state or best like measurement operator. So this is just a recent work we also collaborate with Katie Hero and just published recently. Okay, so that is for we introduce some method we work on, the quantum state tomography, detect tomography, and process tomography. So our focus is more efficient and try to characterize the error and try to characterize the computation complexity. So after recently was we find, okay, so we can develop a unified framework to characterize 3 kind of tomography. So we can find the optimal infidelity scanning. So the first, of course, we need to do some modification for current fidelity. So for the state, they have well-defined fidelity, but for the detector and the process, they use some kind of fidelity, but we find that they have some issues. So we fix that issue, and we try to find the optimal infidelity scanning of 1 over n. So yes, so we, of course, this topic is our active topic in quantum community. So they try to find the optimal infidelity scanning, but a few can be proved, and also they just consider some specific resistance. So we propose a necessary and sufficient condition to achieve this optimal scanning in quantum tomography. This is not just for state tomography, or not just for detect tomography. They could be applied to all kind of tomography. And also we implement some quantum optical experiment to verify the theory and algorithm. So here is some results for the sufficient and necessary conditions. So this is the 2 conditions. So the mean square error should be here with 1 over n, and also the partial eigenvalues of this part, and they should be 1 over n. So one is we calculate, get a theoretical result to characterize when they can achieve the optimal scanning. And another, we propose adaptive and non-adaptive algorithm to achieve this kind of optimal scanning in all state and detector and the process tomography. So we still revise this paper. And also that is a collaborate with Hero and Frank Laurie. So here. So another questions we consider is identifiability of quantum sensor. So for example, we consider here is a spin chain, and now we use one spin as a sensor to interact with the spin chain, and we make a measurement on the first spin. And we want to estimate, we want to determine where this is a quantum sensor is sufficient to identify the system parameter. For example, the coupling strength between the spins and the coupling strength could be different. So this problem, they have some, like the group in quantum engineering group at the MIT, so they discuss this problem and use a globular basis method in this paper, but the disadvantages they find if the n is large, for example, 6, even 6, 7, it's very hard to use their method to determine when it's possible to identify these parameters. So collaborate with them, and we propose a similarity transformation approach. And so imagine, for example, we have the same output data, and we can describe the system. So sorry, so here we use a control series, a state space language. So the same output state, and we can use the two models to describe the output state, output data, and maybe they have different parameter theta. And if we can use the two kind of model to describe the same, explain the same output data, they have to satisfy this equivalence equation, the similarity equation in the matrix. So use this method, we find we don't need to really identify the parameters, but we can convert this into solve this the similarity transformation equation. So we don't need like solve this equation. We try to reduce to consider this one, and then so I mean we don't need to like solve this equation, but we convert this similarity equation. And now if this is the solution for this similarity equation, they have a unique solution. So that means we can determine the parameter, but otherwise we can't really determine these parameters. So use this method, we consider spin system with arbitrary dimension. So for example, this is the exchange model and without transverse field. So this parameter you try to identify, but the n is the dimension, they could be arbitrarily large. So we find using that 1 qubit measurement, we can identify the parameters. And if consider this kind of model, so here they have this the transverse field, and we find if we just can do this the x measurement, sigma x measurement on the first qubit, and that's impossible to identify the parameters. But if we can was do the y measurement, sigma y measurement on the first qubit, it's possible to identify these parameters. So that's the theoretical proof.
Yeah, this result look very interesting. So, but do you have some intuitive explanation of these results?
Yeah, that is a good question. So that's maybe I think maybe it's I think this is a maybe in some sense is tried like so consider the measurement is because here we prepare this like initial state for the this quantum sensor, and this initial state and the measurement they should ensure they can cover maybe in some sense cover the whole state space. So that's maybe so similar like the because this here we use a difference again, and similar is like when we use a measurement for tomography and we need a complete set. So similar like that. But here, because we, this one, we just give a fixed initial state, but we allowed this the like evolve with time. Yeah. Yeah, that's a very good question. Maybe I need to think about it. Yeah.
In this spin chain example,
Yeah.
these your theorems, yeah. So how does this probe spin of probe qubit interact with x? Okay, when measuring x1. So you are measuring the x1, okay, x1 or y1.
Yeah,
Right,
x1, x2, and y1, y2, x2, x3. So that's one dimension spin chain. Yeah.
Okay. And then in theorem 2 and theorem 3, the difference is only either x or y.
Yeah, so there's a measurement, but maybe here I did mention the initial state is the eigenstate of sigma x. So that's the difference. So for example, the initial state is the eigenstate of sigma x, and you just make the x measurement, and then the system involved with time is not enough.
I see.
Yeah.
Okay, so you start from some particular initial state, not the eigenstates.
We started with the eigenstate of sigma x.
Okay, no, so then because of the transverse field, it evolves.
Yeah.
Okay.
Yeah.
Okay. Yeah. Interesting.
Okay. Thank you. So another topic I want to share is quantum autoencoder. We recently work on, and what is the quantum autoencoder? Basically, this is related to quantum data compression. So, for example, we have the classical autoencoder is try to do. For example, we have a big image, and we try to compress into the a small size, and then we can transfer to other place or some like for example laptop, right? But we hope when we can recover with very high accuracy, right? So for the quantum data compression seminar, so for example, we have 4 qubit system. They can encode some quantum data, and we try to compress into 2 qubit, but we hope we can still recover using, for example, if we want to get the information, arrange the information for qubit, and we can recover from this 2 qubit without maybe loss or very small loss, right? So this is the basic idea. Okay, so for example, this is a classical case, and they have encoder. So we have 4-dimension data, and we compress into two dimension, And then we can use the decoder to recover this information. But we hope the recovered information is as close as possible with this original data. For quantum autoencoder seminar, so for example, we have 4 qubits and we use the encoder to compress this one into 2 qubits, and then we use the decoder to recover this to 4 qubit information. And we hope this fidelity between 0 and 0F is very high. So here they have like a reference state. And first, of course, if reference state is simple, and that's be good. And so what I want to mention is for this encoder decoder, we hope this is not just for one kind of specific state. They could be a set of different states. For quantum case, the special for ideal case, this encoder and decoder basically they could be, if they should satisfy the relationship basically is inverse. The UD, the decoder should be inverse of the UE encoder for ideal case, of course. But for classical autoencoder, you don't need satisfy that requirement. So the quantum encoder can save quantum resources and memory requirement because with like less smaller, less I think lower dimension. And this area they have some existing result. For example, some theoretical result and some experimental result in the recent years. And our work basically is focused on one is calculate the theoretical compression rate for quantum autoencoder, and we try to use the learning control method to training quantum autoencoder to find the best, for example, achieve the best compression rate. And our collaborator was also do some quantum optical experiment to verify this result. And recently we consider use a mixed reference state to improve the performance of quantum autoencoder. So we verify on IBM quantum devices. Okay, so the theoretical result here we consider is okay, so the compression rate 1 can be achieved if only if the number of linear independent input state is no more than latent dimension. And otherwise, the maximum also we can calculate the maximum compression rate. So basically, they determined by the sum of partial eigenvalues of the density operator representation of input state. Because here we mention maybe we can a set of input state, we can describe that use a density operator by a similar like a mixed state. And they have the partial eigenvalues for this kind of representation. And other we developed some learning method to training find the optimal encoder decoder. And because of time limit, maybe I skip the details. But roughly speaking, the different machine learning method, for some they get better performance, but some machine learning algorithm they play better than other. So this is our collaborator at the USTC. They also do some experiment to compress 2 qubit to 1 qubit, and they consider, for example, input state, the 2 different kind of input state, and they can use the autoencoder to try to compress the state and get the quite a good fidelity. So other is we find for that case, if we give a set of input state, maybe they have maximum compression rate. So for some case, for example, the complete mixed state, and maybe they can't really compress because this is a upper bound just 0.5. So we find we can before we consider this reference state is fixed, and but also is very simple, for example, zero state. But we find we can optimize this encoder, also we can find the best reference state. The reference state sometimes could be used a mixed state. They can improve the fidelity. Okay, so we consider, for example, this kind of mixed state as a reference state, and also we consider we can use maybe improve the cost function. Also is important to improve the performance. We consider before this the fidelity with the pure state, and if we introduce quantum mutual information as a part of the cost function, we can improve this performance. Okay, so here we do some numerical simulation, consider, for example, similar state. And we have this is A is compressed for 2 qubit system to 1 qubit, and the second is 4 qubit. Yes. So this is we can maybe later on, so we can compare, for example, this one. So this line is the maximum compression rate we can achieve if we choose the pure state as the reference state. But if we can choose the mixed state, and we find we can break this bond, and we can achieve quite good compression rate. And we implement experiment on IBM quantum computer, and we consider compress 2 qubit to 1 qubit. And here we use 4 qubit as the input, because here we need to prepare the mixed state, and we need 4 qubit to prepare the mixed state of a 2 qubit system. And for the reference state, also we use 1 qubit mixed state as a reference state. And we find here the result. This one, the blue one, is like a theoretical bond. If we just use this, use the like a pure state as a reference state. But this is the red one is the experiment result on IBM quantum machine. So you can see the thing break this bond in some range. But the red one is basically use a quantum simulator, because in that case they have low noise, so they can get a better performance. Okay, so that's I think that's all. And also my group also work on other topics like control and optimization of quantum sensor, quantum filtering, quantum smoothing, and quantum robust control, and quantum machine learning, and also other like reinforcement learning related work. Okay, so this talk is based on joint work with lots of excellent collaborators, and I think Enrique is Frank Lorry, Hidehiro Shota, so we have many years collaborators contribution. Yes, so thank you very much.
Okay, thank you very much for your great talk. So now the session is open for question and comment. Is there any questions or comment? Okay, so Tabushi-san.
Talk. I'm not familiar with the autoencoder.
Yeah.
And how do you tune the encoder and decoder with the iterative step?
You mean adjust
Yes.
so each step.
Yes, yes, exactly.
So we like if you say, so normally we use like here we use like machine. Okay, so for the, so here we use like a machine learning to, because when you use a machine learning, of course, they simulate during the learning process. So we can, we try to find the best encoder and decoder. So because this encoder basically corresponds, for example, unitary process. We try to find the best unitary transformation. But when you do this as a experiment, so when you do this experiment, and of course it's every time, for example, you have the output, and then based on output, and you can use like machine learning, you can find okay, so suggest next step is which is the best, and in that way, step by step, they can change the, I think they change this the measure the parameter to control that process. Thank you.
Okay, is there any other questions?
Thanks for the talk. My question is even more elementary, but I just don't simply have a good intuition about this, compression, quantum compression. Can you give some very, example? For example, in this 2-qubit case, you start some input states, RH plus RV. What's the compressed state?
So for example, okay, so this is a 2-qubit state, right? So this is a 2-qubit state, and this is another 2-qubit state. And now what we try to find is, okay, so we find an encoder, and then we input, for example, we have this encoder, we input this state, and we get a 1-qubit state because, for example, okay, so here, so for example, sorry, here is a type. So if we have this 2-qubit state, and we try to compress into 1 qubit and another 1 qubit, so that's that 1 qubit we just ignore. And then we use this reference state, for example, is 0 state, and this is 1 qubit state, and then we recover this state. So for example, we can imagine in raking, we have a 2-qubit state, and then we compress, use this encoder, and we separate, like decouple this 2-qubit state into 2 1-qubit state, right? And then we just keep 1 qubit, the other qubit we just ignore. And then we transfer to, for example, from Riken to Sydney. And Sydney, I just have 1 qubit. And then we use that 1 qubit and another like a reference state that is known, for example, 0 state. And we use that 2 qubit, two single qubit to recover the information, the rho F. And we try to use this rho F. Okay, so we still can get this rho 0.
Yeah, I understand this concept, but I just want to know the simple example. For example, input is, for example, 0, 1 plus 1, 0 state. What is the encoding operation and what is the output compressed state? Can you say that?
Yeah, I think I didn't put the detail here, but it's you can think about like here is a 2-qubit state. Is we can imagine that is for example 4-dimension user vector, right? And then we compress into 1 qubit, but the encoder is 4x4 unitary transformation, and then we, for that input state, use that transformation, unitary transformation 4x4, we get an output state. But for the output state, the vector also is 4. The dimension is 4, right? So we ignore 2 dimensions. We just keep 2 dimensions, another 2 dimensions.
Can you give some concrete example of what the output state and then how to recover? Is there any? I don't get quite good intuition about this.
Yeah, so yeah, maybe later I can show you some example. But here the idea is we have that encoder, and we fix that encoder. That can be used for this input state. Also, they could be used for this kind of input state. Yeah, I can show later. Yeah.
Okay, thank you. Maybe one question from me. I just wonder what's the how it's related to the quantum error correction. Quantum error correction, we have some, let's say, qubit, and we add some redundancy. Then, we recover that is a single qubit information by error correction.
Yeah.
So the process looks kind of similar.
Yeah, that's a very good question. Actually, I think I saw one paper is use this quantum autoencoder to do quantum error correction. So because they have some similarity, but I think they maybe the challenge, like quantum error corrections. Normally, you use a low dimension system. You use a high dimension. So maybe, for example, use a logic qubit, right? So you want to correct the error for 1 qubit. You maybe use many logic qubit to correct the error. But here, I think is normally we have higher dimension and we compress into lower dimension, and then we recover. But definitely, I think they have some similarity. Maybe we can explore.
Okay, thank you very much. Is there any other questions? Maybe from Zoom?
Yeah, I have one general question. So, yeah, in the examples you talked today, you use machine learning for quantum technology, and on the other hand, in your in your group, you also work on quantum for machine learning.
Yes.
So you're pursuing both directions, and what's your perspectives for the prospects for future development of this quantum for AI and AI for quantum?
Yeah, that's the or challenge question. So, but my personal interest is like so before because we use like machine learning to help some, for example, quantum autoencoder or other quantum control problem. Basically, we use a machine learning to help us to design to find the best parameter or something like that, right? Based, for example, it's a unitary operator. Even for also we do some like machine learning for quantum estimation, tomography, so they can help you find the best, for example, measurement. So why is definitely, I think, because now the machine learning become more and more powerful. So definitely we can use that advantage to help us like design, explore, achieve some like quantum, quantum task. That one. So another is they have some good progress. It's like use quantum to improve the performance of the machine learning or AI, right? So that's actually, I will give a talk next week. The University of Tokyo, they have a workshop. But for that one, this moment, I think most people think that is not clear whether we can really like a quantum machine can accelerate, get the quantum advantage for many machine learning. But they do have achieve some like progress, for example. But this is depends how you clarify. Is for example, use a quantum computer to solve like linear equations. So they can achieve quite good performance, right? They can get some quantum advantage. But for other, for example, use a quantum machine, do the neural network, and there's lots of work there. But the problem is they have some challenge. For example, for quantum machine learning or quantum, this is a two challenge problem. One is normally for the classical machine learning, it's the training, if you have data, the training is quite easy, but the generalization is very, very challenging. But when you consider quantum machine learning, basically you use a quantum machine to machine learning. So the generalization, some result will improve. That's quite good, quite easy. But the training become very challenging. Yeah, so I think that I have lots of work to explore, and it's not very clear. But I think the one is AI for quantum. Definitely, they can do something, but maybe not. From like many like quantum physicists, maybe they think that just the engineering problem technically not much like discovery, but they can do something. And for the quantum machine for AI, I think the lots of work to explore, not very clear. Thank you.
Okay, is there any other questions? Okay, if not, I think let's thank Aoi again.
Yes, thank you.
Okay. Okay, thank you very much for joining this colloquium. So next colloquium has not been determined yet, but we will announce soon. Okay, that's all.